Welcome to week 10 of pre-calculus. Our first topic this week is graphs of the sine and cosine functions. So we talked a great deal about these two functions, and it's time that we look at what the graphs of these two functions look like. We will certainly refresh some of the properties of these two functions as we begin using them while drawing their graphs. But let's first recall the definitions. Recall how we defined the sine and cosine functions. We start with the unit circle, whose center is at the origin. And with every real number x, we associate a central angle measured in x radians, where angles are measured from the positive direction of the x-axis. Positive angles correspond to counterclockwise direction, negative angles correspond to clockwise direction. So if we have some positive x, for instance, I can draw an angle measuring x radians. That angle will determine uniquely a point on the unit circle, and the coordinates of that point are defined to be cosine x and sine x. That was our definition of these two functions. So when we draw the graph of, say, sine x, let's begin with sine x, we can recall some of the common values of the sine function. Sine of 0 is 0, because the coordinates of this point are 1, 0. Sine is always the y coordinate. Y coordinate of this point is 0. As we start increasing x in the first quadrant, sine grows up to its maximal value 1, which it attains when x is pi over 2. Halfway from 0 to pi over 2, at pi over 4, we know sine is square root 2 over 2. And also the other two common angles where we know the value of sine are pi over 6 and pi over 3. At pi over 6, sine is 1/2, and at pi over 3, sine is root 3 over 2. So we can start drawing the graph of sine x on the interval 0, pi over 2. At pi over 4, we have root 2 over 2. At pi over 6, we have 1/2. And at the value pi over 3, we have the value of sine root 3 over 2. Naturally, root 3 over 2 is less than 1, because 2 is root 4. So now it's interesting to see what's going on in the second quadrant. Once we reach the angle pi over 2, where sine is 1, and start further increasing x from pi over 2 to pi, the value of sine again starts decreasing from 1 to 0. And here it's very important that we recall the symmetry of sine. What do I mean by this? I mean that if this angle here is x, and I find a point on the unit circle in the second quadrant that is symmetric about the y-axis to this point, so its coordinates will be negative cosine x sine x, immediately we see that this angle here is also x. So what this means is that the graph of sine x will be symmetric about the line, about the vertical line x equals pi over 2. Because if this is x and this is x, then these two angles are also equal. They're both pi over 2 minus x. And at distance pi over 2 minus x, in either side from pi over 2, we have the same value of sine. Because of this symmetry, it's now easy to draw the graph of sine on the interval pi over 2 pi. We just have to imagine we have a mirror along the vertical line x equals pi over 2. And we take this piece of the graph from 0 to pi over 2 and reflect that piece of the graph symmetrically about our mirror to get that piece of the graph. In particular, we will have corresponding to these three special values, we'll have three special values here. Symmetric with respect to pi over 2 to this point pi over 4 is the point 3 pi over 4. Symmetric to pi over 6 will be the point 5 pi over 6. And symmetric to this point pi over 3 will be which point? Well, what is this distance? This distance is pi over 2 minus pi over 3, which is pi over 6. So symmetric to pi over 3 will be the point pi over 2 plus pi over 6. Which is 4 pi over 6 or 2 pi over 3. All right. What happens with the graph of sine once we start increasing x into the third quadrant? We note immediately that in the third and in the fourth quadrant, the values of sine will be negative because the y-coordinates of all points on the unit circle in quadrants 3 and 4 are negative, and sine is defined as the y-coordinate. Well, in the third quadrant, we see that sine will be decreasing as x increases. Sine will be decreasing from 0 to negative 1. And again, we can use some kind of symmetry here. But of a different kind now. If, say, this angle is x, and now say this angle is x, Then, of course, the coordinates of the corresponding point on the unit circle will be negative cosine x, negative sine x. So we can use our piece of the graph of sine x on the interval pi over 2 pi and reflect about the point with coordinates pi 0. For instance, if we know that the graph passes through the point 3 pi over 4, um, root 2 over 2, immediately we see that if I step away from pi by the same distance as pi is from 3 pi over 4 in the right, into the right direction, right? This distance is pi minus 3 pi over 4. And that distance is the same. If I step to the right, I will get the point 5 pi over 4. This distance here is, of course, quarter pi. If I step in this direction by quarter pi, I'll get 5 pi over 4, and by symmetry, I will get negative root 2 over 2. For instance, if I imagine that this angle here, is 3 pi over 4, the angle 5 pi over 4 will result in a point whose coordinates will be, if this is 3 pi over 4, coordinates will be negative root 2 over 2, root 2 over 2. Then the coordinates of this point will be negative root 2 over 2, negative root 2 over 2. We have this kind of symmetry if we imagine a mirror at the point pi 0. So the point 3 pi over 4 root 2 over 2 will be symmetric to the point 5 pi over 4 negative root 2 over 2. In short, if you imagine the origin being here at this point, you can say that the piece of the graph between pi over 2 and pi, and the piece of the graph between pi and 3 pi over 2 are symmetric about the origin. This piece and this piece are symmetric about this point. More precisely, if you step away from this point to the left by some distance x, and if you step away from pi by that distance x to the right, the difference in the values of sines will only be by a negative sign. Sine of pi minus x and sine of pi plus x differ only by a negative sign, which again can be easily seen from the unit circle. This angle is pi. Say this angle is pi minus x, because this is x. Then pi plus x will be this angle. Of course, these 2 points are symmetric about the line, about the x-axis, meaning that they have the same x coordinate, and the y coordinates are equal by absolute value and differ only by a negative sign. So that gives us the piece of the graph from pi over 2 to pi, from pi to 3 pi over 2. And now to get the piece of the graph from 3 pi over 2 to 2 pi, we again know the symmetry. If this angle is x, and we find the point on the unit circle symmetric to this point about the vertical axis, the coordinates of that new point will be cosine x, negative sine x, so that this angle here is also x. We have symmetry of the graph about the line x equals 3 pi over 2. If you reflect the graph of sine x about the line x equals 3 pi over 2, you get a symmetric picture. This vertical line here is x equals 3 pi over 2, and from the unit circle, we see immediately that if you step away by some angle pi over 2 minus x from pi over 2 in one direction, and by that same angle, by the same measure into the other direction, again pi over 2 minus x, that results in 2 points with the same y coordinate. That implies the graph of sine x is symmetric about the line x equals 3 pi over 2. That gives you that piece of the graph. Now we note immediately that since sine is a 2 pi periodic function, we know that sine t equals sine of t plus 2 pi. We know that. We explained in the past that sine is a 2 pi periodic function, and again, it's easy to see this from the unit circle. If you move first by angle t, and then add a full revolution 2 pi, of course, that brings you to the same point on the unit circle, and both x and y coordinates are still the same. On the other hand, that same point corresponds to two different angles, t and t plus a full revolution of 2 pi. Hence, sine t equals sine of t plus 2 pi, and of course, cosine t equals cosine of t plus 2 pi. And you can play that game again and again. It's also sine of t plus 2 pi plus 2 pi, which is sine of t plus 4 pi. And of course, that's sine of t plus 6 pi, and so on. And you can move in the opposite direction, not necessarily in the counterclockwise direction. You can always first move by t, then make a full revolution in clockwise direction. That'll be the angle of t minus 2 pi, and that'll bring you to the same point with the same x and y coordinates. So I can also say that sine t is sine of t minus 2 pi. And of course, I can make another full revolution in clockwise direction to get sine of t minus 4 pi, or sine of t minus 6 pi, and so on. In short, once we get the graph of sine t on any interval of length 2 pi, we can simply copy-paste the whole thing and get the graph of sine x on any other interval. I can literally copy-paste this piece and get the graph of sine on the interval 2 pi, 4 pi, with this being 2 pi, this being 5 pi over 2, this being 6 pi, this being 7 pi over 2, and this being 8 pi over 2, which is 4 pi. And same thing in the direction to the left of the y-axis. In short, we get a graph like this. 0, pi over 2, pi, 3 pi over 2, 2 pi. Let me prolong the x-axis here. Now we get 3 pi here, so 5 pi over 2 here, 4 pi here, and then 7 pi over 2 here, so it's going to look like this. And now if we copy paste that piece to the left, we'll get that piece where this here is negative pi over 2, this is negative pi, this is negative 3 pi over 2, this is negative 2 pi. Next will be, of course, negative 3 pi, and this will be negative 5 pi over 2. And so on. This here, of course, will be next one. Say this is 5 pi, and then this is 9 pi over 2. And you can continue in either direction as far as you want. This, therefore, is the graph of sine x. It's not really a surprise that it extends infinitely in either direction. We know the domain of sine x is the entire real line, so it's something to be expected. And again, this picture at the bottom of the page relates the y-coordinates of points on the unit circle to the points on the graph. This angle here is pi over 6. So the coordinates of this point are root 3 over 2 comma 1/2. And 1/2 being the y-coordinate becomes the value of sine of pi over 6 on the graph. This angle here is pi over 4. And so the coordinates of this point are root 2 over 2, root 2 over 2. And so the y-coordinate of pi over 4 on the graph of sine x is root 2 over 2. Much like this angle is pi over 3. And so the coordinates of this point are 1/2 root 3 over 2. And since the y-coordinate of this point is root 3 over 2, the corresponding point on the graph of sine x has coordinates pi over 3 root 3 over 2. This angle is pi over 2. The coordinates of this point are 0, 1. And the corresponding point on the graph of sine x is pi over 2, 1. All right. Now let's do the same analysis with cosine function. Maybe I should copy and paste this unit circle picture from the previous page. It will be helpful. Again, let's start from the first quadrant and recall that cosine, by definition, is the x-coordinate of the point on the unit circle that corresponds to angle x. Measured is always from the positive direction of x-axis, where the positive direction of angles corresponds to anti or counterclockwise rotation, and negative direction corresponds to clockwise rotation. When the angle is 0, we are at the point 1, 0, and therefore immediately cosine of 0 is 1. As the angle increases in the first quadrant, from 0 to pi over 2, cosine constantly decreases, right? We're moving from this point along the x-axis. X-coordinates get smaller and smaller until the x-coordinate gets to 0 at the angle pi over 2. We again pass through these three special values, pi over 6 when cosine is root 3 over 2, pi over 4 when cosine is root 2 over 2, and pi over 3 when cosine is 1/2. Now, what happens when we are in quadrant 2? We have here a clear symmetry, because if this angle is x, this angle is x. So these two angles are both pi over 2 minus x. We have the x-coordinates of the corresponding points on the unit circle equal by absolute value and different only by a negative sign. That immediately implies that the graph of cosine x will be symmetric about the point pi over 2, 0. So the piece of the graph here reflected upon the point pi over 2, 0 gives us the piece of the graph from pi over 2 to pi. What exactly does that mean? It means if you were to take a point, say pi over 6, this point has coordinates pi over 6 root 3 over 2, the point symmetric about the point pi over 2 comma 0 to this point will also be on the graph of cosine x. And of course that point will be 5 pi over 6 comma negative root 3 over 2. You can check. This point and this point are symmetric about the point pi over 2, 0. What does that mean? It means that it means two things. This point is symmetric to this point about the point pi over 2. That means two things. First of all, that means that pi over 2 comma 0 is the midpoint of the segment joining the points pi over 6 root 3 over 2 and 5 pi over 6 negative root 3 over 2. This distance equals this distance. And I think that's it. So again, you take any point on the graph of cosine x, where x is between 0 and pi over 2. Draw a straight line joining this point and the point pi over 2, 0. Measure from the point pi over 2, 0 the same distance as between the original point and the point pi over 2, comma 0. The point that you obtain will also be on the graph of cosine x. Right here, I can see that the point pi over 4, comma root 2 over 2 is symmetric to the point 3 pi over 4, comma negative root 2 over 2, which of course means that cosine of pi over 4 is root 2 over 2, and cosine of 3 pi over 4 is negative root 2 over 2. So the mirror is at the point pi over 2, 0. And again, what does that mean, that there's a mirror at that point? Take any point on the graph of cosine x between 0 and pi over 2. Join that point and the point pi over 2, 0 by a straight line. Measure along the straight line that distance from the point pi over 2, 0 on the other side. The resulting point will also be on the graph of cosine x. These 2 points are symmetric. Mathematically, that simply means that cosine of pi over 2 minus x, the x coordinate of this point, and cosine of pi over 2 plus x, the x coordinate of this point, are only different by a sign for any x. So that gives us the portion of the graph from pi over 2 to pi. What happens when we keep on increasing x into the third quadrant from the angle pi? Well, we again here have symmetry. This time symmetry is of a different kind, not about a point, but about the line, because if this angle is x, and this angle is x, of course these points share the same x coordinate. And so that means that if you are x radians short of pi, or x radians above pi, the cosine value is the same. In other words, the graph of cosine x will be symmetric about the vertical line x equals pi. That actually immediately gives us the other half, because this half of the graph now needs to be symmetrically reflected about the mirror along the line x equals pi. And that's it. That gives us the portion of the graph from pi to 2 pi. And again, we recall that cosine x is also periodic. With period 2 pi, which implies that once we have the graph of cosine x on any interval of length 2 pi, for instance from 0 to 2 pi, we can literally copy paste that portion of the graph into either direction and get the graph on the entire real line. So the graph of cosine x will look like this on 0 to 2 pi, and I can continue drawing it in either direction. Let me prolong the x-axis. This here, for instance, will be 3 pi, 4 pi, 5 pi, and say 6 pi. And literally copy paste of this portion of the graph will give me that the value at 2 pi is 1. Now, this, of course, here is pi over 2. The value is 0, so therefore the value at 5 pi over 2 will also be 0. The value at 3 pi will be -1. So I get this portion. Then the value at 7 pi over 2 will again be 0. At 4 pi, it will be 1. At 9 pi over 2, it will again be 0. At 5 pi, it will be -1. Then at 11 pi over 2, it will again be 0. At 6 pi, it will be 1. And so on. In the same way, into the negative direction, this here is, of course, -pi over 2, -pi, -3 pi over 2. So next, it will be 0 at -5 pi over 2. And then it will be -1 at -3 pi. And then again 0 at -7 pi over 2. And then again 1 at -4 pi, which is outside the screen. All right, so these are the graphs of sine x and cosine x. And let's summarize what we know about sine and cosine. The domain of each of these two functions is the entire real line, and the image is the interval -1, 1. Both functions are periodic with a period of 2 pi. And that's very, very clear in the graph. Just one important comment here. Do not think that period is the distance between two consecutive zeros. It's a common mistake. Period is the distance between two consecutive peaks or down peaks. This here is the distance of 2 pi. Or this here is a distance of 2 pi. The distance between two consecutive roots or two consecutive zeros is always pi half the period. Same for cosine x. This distance is 2 pi, which is 1 period. This distance is 2 pi. The distance between two consecutive zeros is again pi. This, for instance, is 3 pi over 2. This is 5 pi over 2. The distance between them is pi. It's important to keep in mind symmetry. We know sine x is an odd function. We know that from before. We talked about this in great detail. Because sine x is an odd function, its graph, as expected, is symmetric about the origin. This point, for instance, is pi over 2, comma 1, and this point is negative pi over 2, comma negative 1. Likewise, we know cosine x is an even function. And as we know, the graphs of even functions are symmetric about the y-axis. Right, this point, for instance, has coordinates pi over 4 root 2 over 2. And this point has coordinates negative pi over 4 root 2 over 2. These are symmetric about the y-axis. Much like these 2 points are symmetric about the y-axis. These 2 points are symmetric about the y-axis. These 2 points are symmetric about the y-axis. 2 pi, 1, and negative 2 pi, 1. Once again, the graph of sine x is symmetric about the origin because it is an odd function, and the graph of cosine x is symmetric about the y-axis because it is an even function. All right. We talked about periods. We talked about symmetries. Let's now talk about the so-called sinusoidal functions, which are simply graph transformations of sine or cosine. So a sinusoidal function is a function of the form a times sine of bx minus c plus d, or a times cosine of bx minus c plus d. By the way, I didn't mention one important thing that I believe is worth observing. You can see from the graph of sine x and cosine x that one of them, that they're essentially the same curve, just one of them is a shift of the other. For instance, if I were to shift sine x to the left by pi over 2, I would get immediately the graph of cosine x. That's very important. Shifting the graph of sine x by horizontally by pi over 2 to the left results in the graph of cosine x. Algebraically, that means what? We know a shift to the left by pi over 2 algebraically means that we are adding pi over 2 to x. So because the graph of sine x, when shifted to the left by pi over 2, results in the graph of cosine x, that means that sine of x plus pi over 2 is cosine x. And likewise, if we were to start with the graph of cosine x, we see immediately that if we shift that cosine x to the right by pi over 2, we will immediately obtain the graph of sine x. So shifting the graph of cosine x horizontally by pi over 2 to the right results in the graph of sine x, i.e. algebraically. That means that if I take the graph of cosine x and shifting to the right by pi over 2 corresponds to subtracting pi over 2 from x. And from the picture we see that this is sine x. We can actually explain this one. Maybe we don't yet have enough machinery to explain this one quickly, although we could argue by symmetry. But this we certainly can explain, because if we have cosine of x minus pi over 2, we can factor out the minus now. We can use the fact that cosine x is even, and so the minus inside the cosine function can be ignored. So we simply get cosine of pi over 2 minus x. And that was one of the co-function identities. That really is sine x. All right, so one graph is a shift of the other graph. Sine x shifted to the left gives you cosine x, or cosine x shifted to the right by pi over 2 gives you sine x. All right, let's now talk about more generic shifts and stretches. These occur when we talk about these sinusoidal functions. So here A, B, C, and D are given parameters. We assume A and B are not zero, of course. We pretty much know from our study of graph transformations what these parameters are responsible for. We know the multiplier in front of the function corresponds to stretching, vertical stretching or compression. Right, so if we have the graph of, say, sine x, and you want to obtain the graph of a times sine x, well, we know what to do. We need to first stretch or compress with a factor of a. If a by absolute value is greater than 1, we are stretching. If a by absolute value is between 0 and 1, we are compressing. And if additionally a is negative, we also need to flip about the horizontal axis. This number absolute value of capital A is also called the amplitude. It's the maximum. It's the half the difference between the maximal and minimal value of f. Why is that? Let's explain that. What's the maximal value of this function? Well, the maximal value of sine is 1. So the maximal value of a sine bx minus c plus d is, because the maximal value of sine is 1, the maximal value of this product is capital value of a. Why is that? Well, sine bx minus c is between negative 1 and 1. And if I multiply each side of this inequality by the positive number absolute value of capital A, I naturally get that this is between negative absolute value of A and positive absolute value of A. So the maximum value of this is absolute value of A. And of course, on the other hand, so when we have the absolute value, we have this. When we work without the absolute value, we can work the following way. We can explain this the following way. So it'll be easier. Definitely, any number is smaller, no more than its own absolute value. Now, absolute value of the product is the product of absolute values. Absolute value of sine is no more than 1, and we simply get that this is no more than the absolute value of capital A. And so the maximal value of this expression is simply capital A by absolute value of A plus D. And likewise, any number is greater or equal than its own negative absolute value. which is again negative product of absolute values. Maybe this is here not a good way to state this. Okay. Yes, even easier from the previous line. I can take this inequality here and multiply it by -1. All right, so how does that help me to explain what is the minimal value here? So the extreme values are either 1 or -1, and depending on whether a is positive or negative, the minimal value of this part will be either a or negative a, and in any case it will be negative absolute value of a. Just to think how to obtain this algebraically. So this here is certainly true. All right, we can think about this later, but say if you take a simple example, -2 sine 4x minus 5 plus 7, right? The minimal value of sine is between -1 and 1, so the maximal value of this will be 2, which will occur when sine is -1. And the minimal value of this expression will be -2 when sine is 1. I just don't want to split this into multiple cases. A is positive, A is negative. So we know the maximal value is absolute value of A plus D. The minimal value is negative absolute value of A plus D. So from here, have the difference, 1/2 max over min, simply is 1/2 absolute value of A plus D minus negative absolute value of A plus D. The D's cancel, and we have absolute value of A. So this amplitude is half the difference between the maximal and minimal values of f. That's very important and very useful. And again, I encourage you to think how to algebraically obtain that the minimal value of the expression a sine bx minus c plus d is negative absolute value of a plus d. It's easy when you consider two different cases, a positive, a negative. Another important concept here is the so-called midline. Midline is the horizontal line with respect to which the graph of this function will be symmetric. For the standard sine and cosine x, of course, the midline is the x-axis. Correction. It's not true that the graphs will be symmetric above the midline. Definitely neither sine x nor cosine x are symmetric above the x-axis. What is true is that the line is equidistant from the maxima and minima, right? For the sine x or cosine x, maxima all have y coordinates 1 and negative. Maxima have y coordinates 1 and minima have y coordinates negative 1. So the x-axis is equidistant from these points. For the standard, for the more defined sinusoidal function, a sine x bx minus c plus d, or a cosine x bx minus c plus d, of course, the midline is simply the line y equals d. B and C transform the graph horizontally, shifting or stretching or compressing. A transforms the graph vertically. None of that changes the midline, only the vertical shift does. So without the D, the midline would still be the x-axis. When you shift vertically, the new midline becomes the line y equals d. So here is an example of the function sine x and various vertical stretches with a factor of 2, with a factor of 3, with a factor of 4. Zeros stay where they are. Zeros, remember, are the points of the form pi times k, where k is an integer. So for any constant a sine x equals 0, if and only if sine x equals 0, if and only if x equals pi times k. K is an integer. All right, what about other parameters? Now that we have discussed the meaning of A, the amplitude is responsible for a vertical stretch or compression. Right, this here is amplitude. 4 in this case. What about B? B, as we know, the multiplier in front of x inside the function is responsible for horizontal stretch or compression. And of course, if B by absolute value is greater than 1, we are compressing by a factor of B. And if B by absolute value is between 0 and 1, we are stretching with a factor of 1 over absolute value of B. The period of the standard sine or cosine function is 2 pi. And when you stretch or compress by B, you are, of course, changing the period. For instance, here in the picture, the blue curve is the standard sine x function. The red curve is sine of 2x. So you see we were compressing the function sine x with the factor of 2. Again, if you start thinking of x as time, you can say that the red curve is twice as fast as the blue curve. For the blue curve, it took pi seconds to get to 0. For the red curve, it took half that time, pi over 2. Right now, for the standard sine x curve, it takes 2 pi seconds to get from one peak to the next one. This here is 5 pi over 2. This here is pi over 2, so this distance is 2 pi. But for the red curve, which is twice as fast, it only takes pi seconds to get from one peak to the next one. This here is pi over 4, and this, I believe, is 5 pi over 4. So this distance is pi. The red curve is twice as fast. It has half the period of the blue curve. The green curve is the graph of sine of x over 2, and so we were stretching with a factor of 1 over absolute value of 1/2, which simply is 2. So we stretched the standard blue curve with a factor of 2, and now the green curve is twice as slow as the blue curve. For instance, it takes the green curve 2 pi seconds to get to 0, as opposed to the blue curve, which only takes pi seconds to get to 0. The period of the green curve will be not 2 pi, but 4 pi. If I were to continue the green curve, I would get something like this. So if this is, say, 4 pi and this here is 5 pi, we see that the distance between two consecutive peaks, this distance, for the green curve is from pi to 5 pi, which is 4 pi. So indeed, the period of the green curve is 4 pi, twice the period of the standard blue curve. So B is responsible for amending the period, and in general, the period will be the standard 2 pi period, compressed with a factor of B. Of course, if by absolute value B is less than 1, this really is not a compression, but a stretch. And if B is less than 0, it also means that you are reflecting about the y-axis. Now, what about this number C? What does that change? We know that that affects the horizontal shift, because if we now here write our function a times sine bx minus c plus d as a times sine b times x minus c over b, which is more convenient for us, we see immediately that c over b is a horizontal shift. If c over b is positive, we're shifting by c over b to the right, and if c over b is negative, we're shifting to the left. And in the picture, the blue curve, again, is the graph of the standard sine function. The red curve is the graph of sine of x minus pi over 4. which is the standard sine function shifted to the right by pi over 4. That is the graph of sine x. By pi over 4. And likewise, the green curve, sine of x minus pi, is also the graph of the standard sine x shifted to the right by pi. We can see this in the picture, right? So say for the red curve, the blue curve attains its maximum at pi over 2. The red curve will do this at the midpoint between pi over 2 and pi, which is, of course, 3 pi over 4. The blue curve passes through the origin. The red curve will pass through the point pi over 4, 0, and so on. The green curve is the blue curve shifted to the right by pi. So the blue curve attains its maximum at pi over 2. So the green curve will attain its maximum at pi over 2 plus pi, which is 3 pi over 2, and so on. Interestingly, the green curve also passes through the origin. That is because sine of 0 minus pi, which is sine of negative pi, which also is 0. In fact, if you look carefully at the graph of the green curve, it looks like the graph of the green curve is simply the reflection of the blue curve about the x-axis, which algebraically is expressed by the fact that sine of x minus pi being simply negative sine x, which is interesting. Again, C is responsible for the horizontal shift, and the ratio C over B is called the phase shift. It is important, however, to keep in mind that the order in which you make the transformations is important. We agreed a long time ago that it's better to first perform a horizontal stretch or compression and then the horizontal shift. So when you factor B, you will start with the graph of sine x, then perform a horizontal stretch or compression to result in sine of b x, and then perform a horizontal shift to construct sine of b times x minus c over b. You will be shifting by the value of c over b. That is, of course, c of bx minus c. That is much better than doing things the opposite way. Because if you first shift horizontally and then stretch or compress, you will also be compressing or stretching the shift, which is not very convenient. All right, and now the last parameter d simply is vertical shift, which changes the midline. If d is positive, we're shifting upward. If d is negative, we're shifting downward. Here are some pictures. This here is the classical sine x, and parallel shift by 2 units upward results, of course, in the graph of sine x plus 2. That doesn't change the period. That, of course, changes the midline. The midline here is y equals 2. The midline here is, of course, y equals 0. All right. I don't recommend memorizing which parameter is responsible for what. Simply, if needed, refresh uh, that chunk of material when we talk about graph transformations. A is responsible for stretching or compressing vertically, B is responsible for stretching or compressing horizontally, C is responsible for horizontal shift, and D is responsible for vertical shift. All right, what's left to do is to look at a bunch of examples. In this first example, we need to determine the midline, amplitude, period, and phase shift of the function 3 sine 2x plus 1. All right, so amplitude we know is the absolute value of A, which is, on the other hand, maximum value minus minimal value divided by 2. In our situation, A is 3. So absolute value of A is also 3. The period we know is 2 pi divided by absolute value of B. And B in our situation is 2. So the period will be 2 pi over absolute value of 2, which is just pi. Our function is compressed from sine x horizontally by a factor of 2. So it's sped up relative to the standard sine x. Midline. Remember, midline is the horizontal line that is equidistant from the maxima and minima. If you take a maximum and a minimum, the distance from that line to the maximum and to the minimum is the same. Midline is simply the line y equals d, and d in our situation is 1. And phase shift we know is b over c, or excuse me, c over b, and c in our situation is 0, so there is no phase shift. The graph of this function, 3 sine 2x plus 1, is in the picture. Amplitude is indeed 3. Midline is 1. The distance from the maximum to this line is 3, and so is the distance from that line to the minimum. The distance between two consecutive maxima is pi. So that is the graph of this function. This next example is somewhat more involved. we need to decode the graph given and understand from what function this graph may have resulted. The answer, as you will see in these problems, is not unique. So seeing that this is a periodic function, typical sinusoidal shape, we look for a function of the form a sine bx minus c plus d, or a cosine bx minus c plus d. Essentially, it doesn't matter, because as we know, sine is the same as cosine shifted. Which one you eventually go with, sine or cosine, is absolutely irrelevant. So we can say immediately, doesn't matter which one. And presumably, some of these coefficients, a, b, c, d, we can read off the graph. A, for instance, or rather absolute value of a, being the amplitude, which is half the difference maximum value minus minimum value, is 1/2, because maximum is 1, minimum is 0, so that's 1/2. Therefore, a is plus minus 1/2. What about the period? Period is, on the one hand, 2 pi over absolute value of b. On the other hand, it's the distance between two consecutive maxima. And clearly we see the period is 2 pi. So from here we see that absolute value of b is 1. So b is plus minus 1. I typically recommend choosing b to be positive. We see that midline, again the horizontal line equidistant from maxima and minima, is 1/2. And therefore d is 1/2. To me, this graph looks like reverse cosine, right? If you remember the graph of cosine, reverse cosine will look like this. And our graph looks very much similar to that. So I will prefer to go with the cosine function. Although again, essentially that doesn't matter. So at this point, it's error and trial. Let's say our function perhaps let's try negative 1/2, that's a. Negative because it's going to be the reversed cosine. Positive 1/2 would be like this. That would be positive 1/2. So let's try negative 1/2 cosine b is 1. Let's try without any shift. And plus d, which is also 1/2. So y equals negative 1/2 cosine x plus 1/2. And again, this is A, this is B, this is C, and this is D. And we can easily check a few points here and understand that this indeed is the right graph. We can check y at 0, -1/2 cosine 0 plus 1/2. Because cosine 0 is 1, that's -1/2 plus 1/2, and that is indeed 0. I don't know, let's check pi. Y at pi is -1/2 cosine pi plus 1/2. Cosine pi is -1, so we will get -1/2 times -1 plus 1/2, and that is indeed 1. Let's try, I don't know, -2 pi perhaps. Y at -2 pi, that will be -1/2 cosine of -2 pi plus 1/2. Cosine of -2 pi is, of course, 1, so we get the y value 0. This is a strong indication that we're doing fine, that this is indeed the right answer. Next problem is an example very much similar to this one, and so are the problems on the next page. So it's important that we practice with determining the formula of the given sinusoidal function. So in this example here, again, we will go with sine or cosine, although this to me seems more like a sine function because of lack of a symmetry about the y-axis, but essentially, always remember that sine and cosine are essentially the same thing, just shifted horizontally by some value. So we again look for a function of the form a sine bx minus c plus d, or a cosine bx minus c plus d. Although again, it seems here that our choice will be in favor of sine. But first we find the amplitude, which is on the one hand the absolute value of a, on the other hand it's half the difference between maximum and minimum value. Maximum seems to be 3, minimum seems to be 1. So amplitude is 1, and therefore a is plus minus 1. Period here is on the one hand 2 pi over the absolute value of b. On the other hand, we here see that the distance between two consecutive minima, for instance, seems to be 2 pi, because this here is negative pi over 2, this here is 3 pi over 2, the difference is 2 pi. And so again, absolute value of b is 1, therefore b is plus minus 1, and it's easier if we go with positive value of b. What about the midline? Midline seems to be 2. Therefore, d is 2. And again, my choice is in favor of sine simply because of lack of symmetry about the y-axis. Cosine function is symmetric about the y-axis, so this looks more like something symmetric about the origin shifted somewhere. So I will go with sine. So we should try. For instance, 1, which is a, times sine of 1, which is b, times x, minus 0, which is c. No need to go with any shift horizontally, plus the midline, plus 2. That's d. In short, we suspect our primary suspect is the function sine x plus 2. And again, we should check a couple of points. If we suspect that this is true, y at 0 is sine 0 plus 2. Let's try negative pi over 2. Y at negative pi over 2 is sine of negative pi over 2 plus 2. Sine at negative pi over 2 is negative 1, and so the value is 1. That appears to be true. Y at pi, for instance, is sine pi plus 2, and sine pi is 0, so the y value is 2. That also appears to be true. Y at pi over 2, that is sine of pi over 2 plus 2, and sine of pi over 2 is 1, so we indeed get 3. Which is this point. Looks good. We confirm that the graph given is that of the function sine x plus 2. Let us now look at two functions where we will need to use some kind of horizontal shift. And again, even the statements of the problem directly say that this could be sine or cosine, positive or negative, shifted to the left or to the right. So the answer is by far not unique. That is because sine and cosine are essentially the same curve, shifted in some direction. So this here, to me, looks like a sine curve shifted to the right. And if I had a sine curve like this, and shifted it to the right, or perhaps just downward, I don't know, I would have obtained this. So perhaps I will try some kind of sine curve here. And again, we look for this function in the form a sine bx minus c plus d. So the period here is, on the one hand, 2 pi over the absolute value of b. On the other hand, the distance between two consecutive maxima, for instance, seems to be 6. And so absolute value of b here is 2 pi over 6, which is pi over 3. And therefore b is positive or negative pi over 3. Now, midline. Seems to be the line y equals negative 2. It's equidistant, distance 3 to the maximum and distance 3 to the minimum. So the midline is the horizontal line y equals negative 2, which implies that d is negative 2. And to find the amplitude, we know that on the one hand, the amplitude is the absolute value of A. On the other hand, it's the half difference between max and min. Maximum value seems to be 1. Minimum value seems to be negative 5. So absolute value of A, which is the amplitude, is 3. So A is plus minus 3. So we may try the function 3 for A times sine of pi over 3 for B x minus 2. So here 3 is A, pi over 3 is B, and negative 2 is D. But we clearly see that this will not be the right answer because, for instance, y at 0 is 3 sine pi over 3 times 0 minus 2. Sine of 0 is 0. And so the value at 0 is negative 2. But in our situation, the value at 0 is not negative 2. So the reason why this answer is not correct is because we are missing one more degree of freedom. We did not, at this point, use any horizontal shift. So this doesn't work. And we, in fact, try a more generic function at this point. A is still 3, B is still pi over 3. And now instead of 0 shift, I will try a shift of C, where C is to be found. Where C is to be found. To find this unknown value C, I will, of course, use some of the points on the graph. Typically choose the one that's easy to identify. It seems like it's easy to identify 0.11. So it should be enough information to find C if we know that on the graph, y at 1 equals 1. So if we use that information, we should compute the value of y at 1, which is 3 sine pi over 3 times 1 minus c. minus 2, and that is 1. So that means 3 sine of pi over 3, 1 minus c equals 3, which means that sine of pi over 3, 1 minus c equals 1. And that is logically equivalent if you think about when sine equals 1. On the unit circle. Sine is equal 1 only at this point, and this point is pi over 2 plus any integer multiple of a full revolution. So pi over 2 plus 2 pi n, where n is an integer. So I must then have pi over 3, 1 minus c equals pi over 2 plus 2 pi times n, where n is an integer. And that is equivalent, upon cancellation by pi, that 1 minus c over 3 equals 1 half plus 2n, n is an integer. A little more algebra, multiply by 3, 1 minus c equals 3 halves plus 6n when n is an integer. And from here, if I were to express c, I would have that c is 1 minus 3 half, which is negative 1 half, minus 6n when n is an integer. And I don't need to find all values of c. It's enough to find one value of c. So we may take n to be 0 in this formula, and so c is simply negative 1 half. And now, when c is negative 1 half, I get that my formula for y is 3 times pi over 3x minus negative 1 half minus 2, or in other words, y equals 3 sine pi over 3x plus 1 half minus 2, or even easier, y equals 3 sine pi over 3x plus pi over 6. And we can now check a few points on the graph, see if that's true. We can, for instance, check our point 1, 1, first of all. Y at 1 is 3 sine pi over 3 plus pi over 6 minus 2. Pi over 3 plus pi over 6, as we know, is pi over 2. Which is a good sign because sine of pi over 2 is 1. Pi over 2 is where we have a peak, and this point is indeed where we have a peak. That's minus 2, and that will be 3 minus 2, which is 1. I would also check the point negative 2, where we seem to have a minimum value. So let's check that. y at -2 is 3 sine pi over 3 times -2 plus pi over 6 minus 2. So if we were to compute the argument, -2 times pi over 3 plus pi over 6, what's that? That's -2 pi over 3 plus pi over 6. Denominator is 6. 6 divided by 3 is 2. That's -4 pi plus pi. That's -3 pi over 6. That's -pi over 2, which is also good because that's definitely where the minimum value of sine is. We have 3 sine -pi over 2 minus 2, which is 3 times -1 minus 2, which is -5. Indeed, the value at -2 is -5. Let's compute value of y at 0. Just out of curiosity, we can compute the value of y at 0. So what will that be? Y at 0 equals 3 sine pi over 3 times 0 plus pi over 6 minus 2. So which is 3 sine pi over 6 minus 2. We know sine of pi over 6 is 1/2. And so the y value at 0 is -1/2. That also appears to be believable. The y-intercept is halfway from 0 to 1 below the x-axis. Just one other question that I want to resolve here is the zeros. I want to know what this value is. So where is y0? If I equate 3 sine pi over 3x plus pi over 6 minus 2 to 0, that'll be 3 sine. It's not the value that's easy to understand. So it'll involve arcsine of 2/3, which we haven't yet talked about. So it'll be difficult to find this point. But anyway, we have enough information to see that indeed we have found our function in the form 3 sine of pi over 3x plus pi over 6 minus 2. All right, in this next example, this to me looks like a symmetric function reversed cosine. So negative something times cosine shifted by some value to the left. So the primary suspect will be negative something times cosine, something times x plus something positive. So let's understand what this function is. Following our usual scheme, let's understand the amplitude. The amplitude is on the one hand, the absolute value of a, so we should look for the graph of this function in the form a times cosine, for instance, bx minus c or plus c, that doesn't matter, plus d. And amplitude on the one hand is absolute value of a, on the other hand it's have the difference between max and min. So the max value seems to be 8, the mean value seems to be 0, and so the amplitude is 4, so a is plus minus 4. I believe it's -4 because it looks like it's a reversed cosine. At least that's the most comfortable way for me to think about this. You can also think about this as a sine shifted. That really doesn't matter. There are multiple correct answers to any such question. Anyway, what's the period? Period is, on the one hand, 2 pi over the absolute value of b. On the other hand, the distance between two minima looks like this distance here. This is a little bit short of -1, and this is a little bit short of 9. So this distance here seems to be the same as between -1 and 9, which is, of course, 10. So the period here is 10, which immediately implies that absolute value of b is 2 pi over 10, which is pi over 5. This implies that b is plus minus pi over 5. Now, what about the midline? Again, the midline is the horizontal line equidistant from maxima and minima. Seems like midline is the line y equals 4. Distance to maximum is 4, and distance to minimum is also 4. So, because the midline is at the line y equals 4, we see that d equals 4. But if we try the graph of, say, if we try the function y equals -4 cosine of pi over 5 x plus 4, we can see immediately that this isn't the right answer because this function is clearly even, so its graph is symmetric about the y-axis. Our function is not like that. So our function is that shifted to the left by some value. So the answer is close to this, but not exactly this. So we should look for a function in the form y equals -4 cosine of pi over 5. Now instead of x, I should write x plus c or x minus c, that doesn't matter. X plus c, for instance. plus 4. And look for C now, where C is to be found. So how do we find C? To find C, we, of course, use some of the easily identifiable points on the graph. We can, for instance, use it's a problem here because it's hard to say which points are identifiable. It's hard to say what the x-coordinate of this point is. Anyway, I believe it's easy to understand that this point here is 1, 4, much like this point here is 11, 4. So we can try to find C by equating y at 1 to 4. We believe y at 1, much like y at 11, is 4. And if we compute y at 1, it will be negative 4 cosine pi over 5x plus c plus 4, and that's 4. That happens if and only if cosine is 0. Now, where is cosine 0? We can again use the unit circle. Cosine 0 is at 2 points at pi over 2 plus any number of 4 revolutions in either direction, and negative pi over 2 plus any number of 4 revolutions in either direction, which is pi over 2 plus any number of half revolutions in either direction. So pi over 2 plus pi n, where n is an integer. So from cosine of pi over 5 x plus c being 0, we conclude that this is logically equivalent to pi over 5 times x plus c being pi over 2 plus pi n, and an integer. Upon cancellation by pi, we get x plus c over 5 being 1/2 plus n is an integer. This is logically equivalent to x plus c being 5/2 plus 5n. It shouldn't be x plus c, I apologize. Instead of x, I should have, of course, written 1. One plus c is 5/2 plus 5n, and this is equivalent to c being 5/2 minus 1, which is 3/2, plus 5n, where n is an integer, and we may take any such c. You see, c is not unique. C is not unique. There are infinitely many correct answers for c, which is also not surprising. You could shift that cosine by this much, or by this much plus 2 pi, or by this much plus 4 pi, and you get the same graph. So we may take c to be 3/2 when n is 0. And then our answer is y equals -4 times cosine pi over 5x plus 3/2. It's a good sign, by the way, that c is positive, because we're really shifting to the left. So, and after simplification, we get y equals -4 cosine pi over 5x plus 3 pi over 10 plus 4. We should check at least several points on the graph to understand that our answer is correct. Let's, for instance, check our point 1 and understand that really y at 1 equals 4. So it'll be -4 cosine of pi over 5 plus 3 pi over 10 plus 4. What is pi over 5 plus 3 pi over 10? Well, 5 pi is pi over 5 is 2 pi over 10. So 2 pi over 10 plus 3 pi over 10 is 5 pi over 10. And this simply is pi over 2. Cosine of pi over 2 is 0. And we indeed get 4. So that's good. What about the value of y at 0? Do we get any good value? Probably not, because then we would need to compute 3 pi over 10. I wonder where the peaks are. Probably not at the point 3. Doesn't so appear, but we should check. When x is 3, we get 3 pi over 5, which is 6 pi over 10, which is actually interesting. Y at 3 will be -4 cosine pi over 5 times 3 plus 3 pi over 10 plus 4. This here, 3 pi over 5 is 6 pi over 10 plus 3 pi over 10. That's a problem, nothing interesting. That's 9 pi over 10, which is roughly pi, and so cosine of that value is roughly -1. So this value is roughly -4 times -1, which is roughly 4. And so this value is roughly 8. So this is -4 cosine of 9 pi over 10 plus 4. That's roughly -4 cosine pi plus 4. And that's actually 8. So the value at 3 is close to 8, but smaller than 8. That is also good evidence. So we now can agree that the graph we're looking at is that of the function -4 times cosine of 5 of pi over 5x plus 3 pi over 10 plus 4. The period of this function is 10. The amplitude is 4. And the horizontal shift is negative 3/2. Or rather, well, the horizontal shift is to the left by the value of 3/2. All right, what's left to do here is draw a couple of sketches. The first of these sketches is the graph of the function negative 2 sine of pi x over 2. Let me add a page. We're going to be sketching the graph of negative 2 sine pi x over 2. So rather than drawing it point by point, I think it will be much better if we draw it as a sequence of transformations of the sine function. It's important to practice drawing the graph of classical functions, sine and cosine. So let me draw coordinate axis. All right, so this is the y-axis, this is the x-axis. Now, when making sketches, it's important to choose a good scale. I typically choose 2 cells to be pi over 2. And so every single cell is pi over 4 along the x-axis. But unfortunately, it's hard to keep that scale along the y-axis. So I choose 2 cells along the y-axis to be just 1 unit. Then the graph of sine is easy to draw. And likewise to the left. So this here is pi, 3 pi over 2. This here is 2 pi, 5 pi over 2, 6 pi, 7 pi. This here is the midpoint, 13 pi over 2. And on the left, negative pi, negative 2 pi, negative 3 pi. Accordingly, that's negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, and so on. This is, of course, a 2 pi periodic function. We know that. Period is 2 pi, which is easy to see if you look at the distance between two consecutive maxima, 2 pi, or two consecutive minima. Right, the distance is negative pi over 2 minus negative 5 pi over 2, which is, of course, 5 pi over 2 minus pi over 2. That's 4 pi over 2, that's 2 pi. And now, after that, we're going to be drawing the graph of sine of pi over 2x. So this will, of course, be simply a horizontal compression with a factor of pi over 2. So let me draw a new set of coordinate axes. So again, the transformation we're applying is the following. We're going to be horizontally compressing by a factor of pi over 2. Of course, pi over 2 is greater than 1. So we're speeding up our function. The period will be smaller than 2 pi after that. So again, let's keep track of our scale along the x-axis. So this here we had 2 squares horizontally. That's pi over 2. Let's keep here a different scale. This time, let's say 1.5 squares will be pi over 2. So that 3 squares will be pi. Here, 4 squares corresponded to pi. And in our situation, we have 3 squares corresponding to pi. This is not reflecting the actual change in scale, because when you compress by a factor of pi over 2, it will not be the compression that'll make the distance of 4 squares into the distance of 3 squares. So I'm not really keeping the actual scale correct here. Definitely 4 divided by pi over 2 is not 3, right? It's not true. But for the purpose of making a good picture, I would like to choose this scale. Again, 3 squares will be a distance of 2. Here, 4 squares was a distance of pi. So here, 3 squares will be a distance of 2. So this is then 4, this is 6, this is 8, this is 10, this is negative 2, this is negative 4, negative 6, negative 8, and so on. So this is then 1, this is 3, this is 5, 7, 9, -1, -3, -5, -7. And so at 1, we will have at 1, 3, 5, and 7, we will have maxima and minima. At 2, 4, 6, 8, and 10, we'll have our zeros. So the graph will look like this. So as expected, it's faster than the original graph. So on the left, accordingly, it will look like this. The period here is what? This is the graph is of the function sine of pi over 2x. And so the period here is 2 pi over absolute value of b, which is pi over 2. So that's 2 pi over pi times 2. And that simply is 4. And 4 is, of course, less than 2 pi. So indeed, our function has a smaller period. It's 4 periodic, has a smaller period, so it's faster than the original graph, than the original function. And again, don't mind the scale. Here we have the scale in which pi is 4 squares. Here in the second picture, we have a scale in which 2 is 3 squares. And of course, I don't mean to say that pi over 2, pi divided by 2 equals 4 divided by 3. Of course, that's not true. So the scales are really different. They're relatively close, but of course not equal. Now, the next transformation will be stretching this vertically by a factor of 2. We may keep the same scale along the y-axis and the same scale along the x-axis. So let me draw a new set of axes. Here we will also have distance 2 along the x-axis to be 3 squares. So we will have 2, 4, 6, 8, and 10, and -2, -4, -6, -8, and accordingly 1, 3, 5, 7, and 9, and -1, -3, -5, -7, and -9, Just a second. Something somewhere -7, -8. Yeah, that's enough. So, but now the amplitude is not 1, the amplitude is 2. So the graph will look like this. And accordingly, on the left, that is 2 sine pi over 2x. It is again 4 periodic, and the transformation that we did was vertically stretched by a factor of 2. And to get the desired graph now from this one, we need to put a minus here, which will correspond to flipping the graph about the x-axis. All right, so the graph will accordingly look like this. We reflect about the x-axis. Maxima become minima and vice versa. And that is what the graph of -2 sine of pi over 2x looks like. So the transformation that we did from last step was simply reflect about the x-axis. All right, now the second sketch. The second sketch was that of the function 3 sine pi over 4x minus pi over 4. So that will be slightly more complicated. We will have to be very careful with our scales. Let me add a page after this one. Three sine pi over 4x minus pi over 4. So let's develop a plan. The plan is this. We will first draw the graph of sine x. Then we will horizontally sketch to account for the factor pi over 4 in front of x. So that will result in the graph of sine of pi over 4x. So horizontally stretch, because pi over 4 is less than 1, we stretch horizontally by a factor of 4 over pi. So we will slow down our function. It will be with a period greater than 2 pi. The period of this function, as we will see, will be greater than 2 pi. Then we will produce the function we will produce the graph of the function sine of pi over 4x minus pi over 4, which I'd rather write as sine of pi over 4 times x minus 1. And here the transformation will be a horizontal shift to the right by 1 unit. So it's always easier to first horizontally stretch or compress and then horizontally shift than vice versa. Because if you're first shifting and then stretching compression, you're also stretching compression the shift. You have to be very careful here. But then we are simply vertically stretching by a factor of 3. And that will produce the graph of 3 sine pi over 4 x minus 1. All right, let's start with the classical graph of sine x. And the scale will, as before, be 4 squares corresponds to pi along the x-axis. So the graph will look the following way. So the scale here is 4 squares corresponds to pi, or which is the same 2 squares corresponds to pi over 2. All right. Now we stretch horizontally. This function here is 2 pi periodic. We want to obtain this function. What will be the period of that? Well, the period of that will be 2 pi over the coefficient in front of x, which is pi over 4, which is 2 pi over pi times 4, which is 8. And of course, 8 is greater than 2 pi. So our function will be slower than the original one. So the scale that I will choose will be the following. I will choose 5 squares to be 4. We will see what that means. All right, so along the y-axis, nothing will change. And so at 5 squares, I will have my 4 units. Because the factor in front of x contains pi, we'll now be measuring in standard units, not in fractions of pi. And I need to make my function slower. So let's say this here is 4. So the scale I'm choosing is 5 squares is 4 is 4. So 1 square is rather one. If we divide this by 4, 1.25 squares is 1 unit. Here above, the scale was what? 4 divided by pi squares was 1 unit. Our goal is to create the impression that the graph is that of the function which is slower than the original one. So then this will be 8, and 5 more squares will be 12. So this then will be 2, this will be 6, this will be 10, this will be negative 4, this will be negative 8, this will be negative 12. So this is negative 2, this is negative 6, and this is negative 10. And the graph will look the following way. If this here is 2 pi periodic, this here is 8 periodic. And of course 8 is greater than 2 pi. So this function is slightly slower than the original one. So the transformation was horizontal stretch horizontal stretch, correct, horizontal stretch by a factor of 4 over pi, which is greater than 1. The next transformation will be a shift to the right by 1 unit to produce this graph. So a new set of coordinate x's. And we simply try to mentally imagine shifting this thing to the right by 1 unit. So all with the same scale. There's no need to change the scale horizontally because we're not compressing or stretching horizontally. So for instance, instead of points 2, 4, and 6, we should pay attention to points 1, 3, and 5. So where will be point 1, for instance? Because 2 is slightly above, is slightly more than, 2 is exactly, 1 is 1 1/4 squares. The scale remains the same. We can copy and paste this. The scale remains the same, so 1 1/4 will be 1. And then 3 will be 3 times 1.25, that's 375 squares. Then 5.125. What is that? That's 5. That's 5 times 5 quarters. That's 25 quarters. That's 6 plus a quarter. Slightly above 6. It'll be 5. Then where will be 7? Well, 7 is only 2 units more than 5. It's easier to compute, actually. 7 times 5 over 4. That's 35 over 4. That's 8 plus 3 quarters. Next point of interest will be 9. 45 quarters. That's 11 plus a quarter. Slightly above 11. 11 will be 55 quarters, and the closest, I believe, is 52. That's 13 plus 3 quarters. Something doesn't feel right. That's 11. And 13. That's 65 quarters. That's 64 over 4. That's 16 plus a quarter. All right. And so at 1 we have a max, at 3 we have a, excuse me, vice versa. We shift this to the right. At 1 we have a 0, at 3 we have a max. And at 5 we have a 0 again. All right. What happens on the left? Again, we're shifting to the right, so all these numbers should also shift to the right. So let's recompute them. So negative 1 will simply be negative 1.25. So 1 and a quarter to the left. Next will be negative 3. So negative 15 quarters. That's negative 3 and 3 more quarters. Then we will have negative 5. Negative 15 quarters. That's negative 25 quarters. That's negative 6 and 1 more quarter. Now negative 7, that's negative 8 and 3 more quarters. Next is negative 9, that's negative 45 quarters. That's negative 11 and 1 more quarter. And negative 11, that's negative 55 over 4. That's negative 13 and 3 more quarters. Now the value, okay, at 0, the value at 0 of this function. When x is 0, we get sine of pi over 4 times 0 minus pi over 4, so that's negative root 2 over 2. A difficult value to graph, so we will not pay attention to it. All right, so negative 5 is the next peak. This is the graph of sine of pi over 4 times x minus 1, which is the same as sine of pi over 4x minus pi over 4. And now we simply stretch this vertically by a factor of 3. So this transformation again was a shift to the right by 1 unit. And 1 unit in our scale is 1.25 squares. All right, so let me draw another set of axes. The horizontal scale stays the same. This here is 1, this here is 3, 5, 7, 9, 11, and 13. And likewise, -1, -3, -5, -7, -9, and -11. The only change is the amplitude. Instead of 1, it's now 3. The scale, by the way, stays the same, so I should copy this. And this is the graph of 3 sine of pi over 4 times x minus pi over 4. So the transformation performed from the last step was a vertical stretch by a factor of 3. All right, this finishes this example. And the last example in this chunk of material is this application example. We have here a circle of radius 3 mounted with its center 4 feet off the ground. The point closest to the ground is labeled P. Sketch a graph of the height above the ground of the point P as the circle is rotated. Well, we're not told in which direction it's rotated. Assume, as always, the rotation is Doesn't matter, clockwise or counterclockwise. We'll think about it. Then find a function that gives the height in terms of the angle of rotation. All right, so what can we say about the sketch? Let me draw the coordinate axis. If we start counting time at the moment when p is at its lowest position, we start at the minimum, and because this distance is 3 and the entire distance is 4, the height at this point in time is 1. So the minimum value is 1. Then we start rotating the wheel, the circle. I don't know in which direction. I don't know if it matters. Say in that direction. The height of the point starts increasing to its maximum. And maximum is where? Maximum is at this point. And because this distance is 3, and this distance is 3, and this distance is 1, this distance, at this point, the height of point P will be 7 feet off the ground. At what point will that happen? Let's, for simplicity, rotate the circle in the positive direction as we always do. So at this point, the height is 7 feet, but what angle corresponds to this point? When we rotate point P by an angle of pi over 2, P will be here. Here, the angle will be half a revolution, which is pi. So at point pi, our function takes value 7. At point pi over 2, our function takes value 4. And at point 0, when the angle is 0, the value is 1. When the angle is 3 pi over 2, the value is again 4 feet. So the sketch is then this. This is 0. This is, say, pi. This is pi over 2. This is, say, 2 pi. This is 3 pi over 2. And by the way, at value 2 pi, we are again at the lowest position, so the value will be 1. So f will be 2 pi periodic. So say this is 7. Okay, so this distance is then 6. Halfway will be 4. So at pi we have value 7. And at pi over 2 and 3 pi over 2 we have value 4. And then, of course, it goes the same way. It's 2 pi periodic. So what is the formula for this function? Well, to me, it looks like a reversed cosine. So let's look for this in the form a cosine bx minus c plus d. B is 1 because it's 2 pi periodic, since f is 2 pi periodic. What about the midland? What about D? D is 4 because that's where the midland is. So this distance is 3. And this distance is 3. D is 4 since the midland, the midline is y equals 4. Now, the amplitude clearly is 3. So A is plus minus 3. And I would like to try negative 3. Because to me that looks like a reversed cosine. Positive cosine would look like this. Negative would look like this. And I want to try negative 3 cosine 1 times x without any horizontal shift plus 4. So in other words, y equals, this is A, this is B, this is C, this is D. So y equals negative 3 cosine x plus 4. And indeed, the graph would look like this. At 0, it would have its minimum. Value is 1. At value pi, when cosine is negative 1, we will have maximum 7, and so on. So this is the candidate for the right answer. The only question is, that I have at least, does it matter in which direction we rotate? If we were to rotate this in the positive direction, what would have changed? That's a question for you to think and to discuss with your peers. And we are done with this example because this is our correct answer.